Okay, so switch to this. Okay, so let us continue. Uh, okay, so yesterday we have seen how we can embed the description of a Turing machine, including all the components in the form of a string over 0, 1 binary encoding. Okay. Exact encoding that we use is not very important. Only thing is that if that encoding is fed to another Turing machine, not in its head, but in its memory, then by going back and forth, it can make out what is happening. Right. So that's the important thing. Okay, so let me just summarize this. So this was some kind of encoding that we have used. Anyway, this is some encoding of our choice, but we can go for any other encoding. Okay. Okay. Now, I will design a machine eventually that, given an encoding of a Turing machine and some input for that machine, will simulate that machine M on that input, and will do whatever that machine M is supposed to do, and eventually give some accept, reject decision or looping. Okay. So, but before doing that, let us convince ourselves that uh, if we are given some binary string over 0, 1, okay, some binary string, we can still think of this as a Turing machine. Okay. Why? The point is that not all binary strings stand for valid encodings, right? And this validity can be checked by a Turing machine. Okay. By moving back and forth. Okay. You can first find the number of states, the different alphabet sizes, and so on. Check which one is, everything is in order. And then one by one, it will check all the transitions. And we'll simply find out that delta PA. So P is in the correct range, A is in the correct range, and our output is Q, B, some direction. That can figure out whether Q is in the correct range, B is in the correct range, and direction is either 0 or 1, whatever. So that is some kind of semantic checking. Even the format can be checked, whether the input provided as the encoding of a Turing machine is syntactically correct. Okay. But then, if some string does not correspond to a valid encoding, which a Turing machine can check, we will assume that this is a special machine. Okay. So any string can be treated as a binary encoding of a Turing machine. If it is not valid, then we can simply make the assumption that it stands for a Turing machine, which upon any input immediately halts, rejects and halts maybe. Some kind of assumption like that. Okay. Not assumption, I would say, some kind of convention like that. Okay. So with this convention, every binary string becomes a Turing machine. Okay. One thing you see that So this particular machine, this also has a valid encoding, but given any invalid encoding, it will stand for this machine. Okay, so that essentially means that this machine, this particular machine, has multiple encodings. In fact, it has infinitely many encodings, okay, because there are infinitely many invalid strings. But this will not actually matter in the proof that I will tell. Okay. Uniqueness of encoding is not really a necessity for the proof that we are going to see. In fact, even you can say that these valid encodings are also not unique. Why? Because you have some states like S, R, T, PQ, right, UV, okay. And we have given some numbers 0, 1, 2, n minus 1. Always change this numbering. Start state is 0 in one, start state may be 1 in another encoding. Okay. So that way, the same machine may have multiple encodings. So this delta things, the transition entries, they may also be permuted. Okay. It is fine as long as I have all the transitions in some order. So the valid encodings are also not unique. Okay. So for a given Turing machine, there are multiple valid encodings. Okay. Again, the thing is that this will not matter. Uniqueness of encodings is not needed in the so-called diagonalization proof that we are going to see shortly. Okay. The important thing is that any Turing machine can be encoded in the form of a binary string. And the second important thing is that any binary string can be thought of as the encoding of a Turing machine, even if that is invalid. Okay. Okay. Likewise, any binary string can be treated as the encoding of some input for that Turing machine. So if you look at that encoding, so it is 0 power the number that we have given for the first symbol, followed by 1, 0 power something followed by 1, and so on, right? That are for a given Turing machine may be out of range. If there are, for example, k symbols, and you have something like k or k plus 1, 2k, k square, a 0 power that thing, that does not stand for any valid symbol, right? Okay. So, of course, this encoding is very much dependent on the machine that we use. But the point is that encodings of strings can also be invalid. Okay. So once again, I make some assumption that if a string does not correspond to a valid encoding for a given machine, maybe it stands for epsilon, the empty string, because we cannot make out anything out of that description. Okay. So if W is invalid, oh, sorry, we should take W equal to epsilon, not X. Okay. Actually, I have used both W and X here. Anyway. Oh, no, it's okay. W is the encoding, X is the string. Okay, if W is encoding, we can take X equal to epsilon. Okay, anyway. So once again, any string for any machine can be encoded as a binary string. Conversely, any string can be thought of as the encoding of some string. Again, this is not necessarily unique. Okay. This will not matter. Okay. Again, the same thing, multiple encodings, whether valid or invalid, may represent the same string X, and it doesn't really matter. Okay. Then the proof that we are going to see. Okay, so now there should be some kind of notational thing. If I call a machine M, okay, M is not exactly same as the encoding of M. M is a machine, right? Some kind of mathematical or physical entity. Okay. Whereas its encoding is basically a binary string. It stands for the same thing. Okay. But they are not exactly the same thing. Okay. So one possibility is I can denote the encoding of M or X using a pair of triangular brackets. Okay. But we will more often than not do this. Okay. This is basically an abuse of notation. So whenever I talk about M, I mean two things, that physical machine or mathematical entity itself and also its encoding. Okay, the context will make it clear whether I am talking about that machine or its encoding. Okay, so whenever I write M and X to the tape of a Turing machine, the so-called universal Turing machine, of course I am talking about the, I am not drawing a picture of that machine in some form on the tape, right? Okay. But whenever I say M does this, M enters its accept state, then I am essentially talking about that particular machine itself. Okay. So be careful. So M and its encoding are different things, but we will write the same thing, M, to denote this. Both of this. Yeah. Yeah, you make some convention. Hmm. No, that's what I mentioned. Epsilon also has a valid encoding. Okay. And the strings that do not stand for any valid encoding, I make some kind of convention. Okay. And that convention is that I can take it as the empty string. And epsilon has many, many encodings. That's true. That's what I mentioned there, right? So multiple encodings may represent the same string. Okay. But multiple encodings of a machine or a string do not pose a problem. Okay. The only thing is that every string has a valid encoding and every binary string can be thought of as the encoding of something, even if invalid. Okay. The uniqueness of encoding is not a botheration for us for the so-called diagonalization proof that we are going to see. Okay. And you see that even valid encodings are not necessarily unique. Right? Hmm? Yes. You can renumber the symbols. Okay. And then the things change. Okay. So these things are not issues that we should bother about. Okay. Okay. So now comes the I would say eventual goal of designing a machine that can solve all the problems. And that machine is called the universal Turing machine. Let us reserve its this symbol capital U to stand for this universal Turing machine, or UTM in short. Okay. So U, given M and X, but more precisely given the encoding of some Turing machine M and an input string X for M, you will simply simulate the working of M on X. Okay, but the difference is that from earlier applications or earlier examples is that this description of M and X now appear on the string on the tape of this universal Turing machine. Okay. In fact, there are infinitely many Turing machines. Therefore, you cannot this machine U cannot store the definition or I would say, yeah, definition of every possible Turing machine in its head, in its CPU or finite control, because it's a finite size. Okay. Maybe very large, but still finite. Okay. So the input, okay, for that matter, I can design it as a three-tap machine, three-track machine or whatever. That's not very important. M and X are input. They are both binary strings, but somehow I have to separate those. Right. That can be done using a special symbol like hash. Okay. Encoding of M followed by some separator hash followed by an encoding for the input X for M. So these three things, two encodings separated by a hash, form the input of the universal Turing machine U. Okay. So essentially this is the exe file, and when you run M, you get the input from this part. Okay. Okay. For the moment, we can assume that M is a deterministic Turing machine. If it is a non-deterministic Turing machine, I can always convert it to a deterministic Turing machine, equivalent one, and work on that. Okay. Okay, so you uses its second step to simulate the tape of M. Okay. And it uses the third step to do some kind of, I would say, rough work. Okay. For example, yeah, in this case, it's storing the state of M and the head position. Okay. An alternative possibility is that you can store the configuration of M on a single tape. That is another possibility. The only difficulty in this case is that this is not exactly compatible with our encoding scheme, because states are numbered 0, 1, 2, 3, blah, 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 and symbols are also numbered 0, 1, 2, 3. Okay. So it's very difficult to distinguish between, actually not difficult, it's impossible to distinguish which is a state and which is a actual symbol from gamma. Right. So because of that kind of encoding, of course I can make the two things different by a slightly different encoding. Okay, that can always be done. And if I do so, then I can write the configuration of this M on a single tape. But anyway, it doesn't matter. I can use another tape to store the state and head position, this two information. Okay. Then, okay. For example, you may first check whether M, the encoding M given on the first step is a valid encoding. If not, it knows that the corresponding machine M stands for something that immediately rejects and halts. So U also does the same thing. Okay. And again, it will also make a sanity check about the validity of the encoding for X. If it is not valid, it can simply erase that X part and assume that the input is epsilon. Okay. So this is the initial sanity check. Not a big issue actually. Otherwise, if m is valid, x is valid, it will initialize the second step to stand for the initial situation or initial configuration for m. So that means x is provided as an input to m. So x is copied from the first step to the second step. Okay. And the initial state is s. So whatever the encoding for s is, it reads from that description, copies that to the second step. And this is followed by the initial head position, which is at cell number 0. Happy? So this essentially prepares you to start the simulation of m on x. Okay. Then let us see how each step of m on x can be simulated by you. Okay. So just one step I will tell, and that thing is repeated multiple times until m reaches a conclusion. And if m does not reach a conclusion, it continues looping. The simulation will also continue to loop. Okay. Okay, so each single step. So its transition is of the form delta p comma a equal to q comma b comma d, right? So it gets p from the third step. Okay. And it gets the head position also from the third step. So based upon whatever is written on the third step, it will realign its second head to that cell. Okay. And it will read that symbol. Okay, so you also knows the head position from the third step. You align it head to point to the HH cell is not exactly correct because symbols are encoded like 0 power something. So it's not exactly the HH cell. Okay. Anyway, it can go there, head position, and HH symbol is better. Okay. And finds out whatever is there. So A is red, P is red. Okay. And then what M does, it now scans the description of M on the first step. Okay. So it knows the current state P of M. It knows the symbol that is scanned by the head of M, which is A. Then, assuming that this is a valid encoding, there will be a unique transition of the form delta P comma A written on the first step. Okay. So once again, it locates the 0 power P power 1, 0 power A entry on the first step. Okay. So you replaces, okay, so it finds that P is known, A is known. So it now scans the first step, finds out what Q is, what B is, and what D is. Okay. Then you replaces A by B. Actually, 0 power A by 0 power B. Okay. This is how we have encoded things. On the second step. And that means you may have to relocate everything because 0 power A and 0 power B may be of different length. If A is not equal to B, they must be of different length. So everything to the right may need to be relocated by the difference A minus B or B minus A, whatever is relevant. Likewise, you replace P by Q on the third step. And then looking at the direction D, it either increases or decreases the position of the head on the third tape, right? Depending upon the direction, left or right. If you want to keep stationary there, you may keep it. But anyway, you changes the head position of M on the third tape. Okay. So this is basically a complicated procedure, moving back and forth to locate things and all that stuff. But given sufficient time, you can do that. Okay. It's not an elegant way of doing things, right? Because we do not have random access memories. Okay. So your tape is very sequential. You can only move back and forth to look at things. Okay. Anyway, so this completes the simulation of U, simulation by U of one step of M. Okay. So what is the final conclusion about U? First of all, U is a Turing machine itself. Okay. So it has its own language. Okay. Now, before knowing that thing, let us see how U accepts or rejects. Okay. So if the simulation of M ever enters the accept state T for M, U also immediately accepts and halts. It goes to its own accept state. Let us call it T prime. It goes there and halts. Okay. Likewise, if M ever enters its reject state, R, U also immediately enters its own reject state, which may be R prime, and halts. Okay. Otherwise, the simulation keeps on running. Okay. So if M loops on X, then this simulation keeps on running because it never enters T or R. Okay. So you continues simulating the steps of M forever. Okay. So if that is the behavior of U when presented with M and X, then you see that U is designed to detect whether M accepts X. Right? That is the only situation when U also accepts. If U explicitly rejects, if M explicitly rejects, U also explicitly rejects. If M loops, U also loops. Okay. So this means that U essentially solves the membership problem given a Turing machine M and an input X for M. Okay. So in other words, I can write the language of U as MP. Okay, MP is actually a language, not a problem. But this name, this abbreviation comes from this understanding, derives from the membership problem, MP. So what does it accept? A set of all encodings of M followed by all encodings of X, such that M accepts X. Okay. So M hash X such that X is in the language of M. Sometimes we also write it mathematically as a set of all pairs M comma X such that X is in the language of M. Okay, so we will follow this M hash X notation, but some books follow the second notation. Okay, M comma X. So the language of U is called the membership problem, MP. Okay, it's a language, not a problem actually, but every problem is essentially the same as a language. Okay. Okay, so U solves the membership problem or recognizes the language MP. Now, I can slightly change the behavior of U to accept a slightly different language, and that is going to be very, very important for the rest of this lectures. Okay, it is slightly modified to another kind of universal machine that does not just check the membership of something. On the other hand, it checks whether the simulation halts or not. So if the simulation ever enters the state T or R, prime now accepts and halts. Happy? And if M does not halt on X, then the simulation also does not halt. It's a kind of implicit reject. Okay. So it's something like this. M never enters. If ever enters T or R, U prime accepts. Okay. So U prime accepts even if M enters R, which is basically an explicit reject for M. But this entering T or R is the halting condition for M. Okay, so instead of checking membership, it is now solving what is called the halting problem. Okay. So I use the abbreviation HP for halting problem and define this language HP, language of U prime, M hash X, such that M halts on X. Okay. And as I mentioned, some books write it as a tuple, as a pair, M comma X, as that M halts on X. Okay, so we now have two problems or two languages, MP and HP. Because these languages are languages of Turing machines, they are definitely recursively enumerable. So MP and HP are recursively enumerable. The immediate question that now comes is, are these languages recursive? Okay. So MP and HP are languages of Turing machines, and therefore they must be recursively enumerable. So the immediate question is that, are these languages recursive? One thing is that the universal Turing machine is not a total Turing machine. Agree? Because it blindly simulates the working of another machine on its own input. Okay. And if that machine decides to loop, the simulation will also loop. So this is not a total Turing machine. Okay. But that immediately does not imply that the language of is not recursive. Why? Because it is a particular Turing machine, right? And let us think of a machine that accepts nothing. Okay. So this Turing machine, like that invalid thing, invalid encoding thing, we immediately go to the reject state and halt. Okay. There is another possibility. Given any input, the machine will simply keep on moving right. That's an infinite process. That is also another form of reject. It's not explicit reject, it's implicit reject by never saying accept or reject. Okay. Both these languages both these machines accept the same language, phi, empty set. So one Turing machine, which is total, the first one. It is the Turing machine, the second one, which is not total. Okay. So having a non-total Turing machine for a language does not immediately imply that that language is not recursive. Okay. So the question now comes about this HP and MP. Are they recursive? So what U does, it does a kind of blind simulation of M on X. It does nothing more, I would say, complicated than a blind simulation. Whatever M is supposed to do, you will keep on doing that. Right? Appears to us. Yeah, so in particular, if M does not halt, the simulation also does not halt. Okay. So U is a recognizer, not a decider. Okay. But the question is that, is there a more intelligent way than blind simulation to decide whether M accepts? Blind simulation is one way, definitely. But it need not be the most efficient or most intelligent or the only way of solving the membership problem or the halting problem. Okay. So that is there are many special cases whereby looking at the encoding, you may decide, you or any other Turing machine that tries to solve the membership problem can decide whether M is going to halt on X or M is going to accept X. Okay. So for example, if the encoding of M is invalid, there is no need for any simulation. Okay, an encoding, validity of an encoding can be checked at the beginning. Okay. So this is one situation. And if M has no transitions that lead it to the accept state, then also it's never going to accept the accept state. And that these things can be simply obtained by looking at the encoding. Okay. No need for doing any kind of simulation. If there is no delta PA of the form T, PD. Okay. And you can also think of another specific situation like this. So let's say M never writes some kind of symbol capital A to its step, but the only way it can go to state T is by transitions of the form delta PA. Okay. A is not part of the input alphabet. It is not the left end marker or the blank, but then from where will A come? Okay. Unless the machine itself writes somewhere. If it never writes capital A and it requires capital A to go to the final or accept state, then this is never going to happen. And these are some, I would say, specific situations which a machine for the membership problem can check. Okay. And this is possible by looking only at the encoding. No simulation is needed. Right. But as you see that there are many such things, right? Okay. So, and so on. There are many such things. So these are much more intelligent than just doing simulation. Let's do some kind of maths on the encoding given and decide in a finite amount of time whether M is going to halt on X. Okay. But the reality is that in general, this ... means that there are many such special cases. Okay. The idea is that in general, there is no better way of solving the membership problem or the halting problem than doing blind simulation. There are special cases, but there are infinitely many of these special cases. All these things cannot be checked. Okay. But this is basically a very loose statement. In general means you leave out all the special cases that you need to handle, finitely many of them. Beyond that, there is no general way for a Turing machine that accepts MP or HP other than simulating M on X. Okay, but proving such a statement is actually, I would say, some kind of difficult, because this is not exactly a very mathematical statement. Because in general is nothing quantified. We cannot quantify it mathematically. Okay, but what is provable mathematically is this statement. Okay, so the membership problem is not recursive. It is definitely recursively enumerable because it is the language of a Turing machine, but it is not recursive. And this thing we can prove because this is a precise mathematical statement. Okay. And the same thing is true for the halting problem, HP. Okay. So this is what we are now going to see. In fact, I will give some kind of diagonalization proof for the halting problem. You can very easily adapt that proof to the membership problem. Okay. Okay. So I will now prove that the halting problem is not recursive. So let us prepare for this proof. Okay. The first of all, this almost the same proof works for the membership problem with a little bit of changes. Okay. Now comes the encoding issues. We have encoded Turing machines as binary strings. That is strings over 0, 1. Okay. And the set of all such strings, that is basically 0, 1 star, that we know to be countable. Okay. Therefore, I can make an exhaustive listing of all these strings in 0, 1 star. Okay. What that listing exactly is not very important. So I can do it. Alpha 1, alpha 2, alpha 3, this is the first string, this is the second string, this is the third string. Of course, it's an infinite listing, but every string will eventually come. For example, it may be epsilon 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0. Okay. This is one possible way of listing all the strings. Whatever it is, it's not very important, but I can make exhaustive enumeration, although infinite, of all the strings over 0, 1. Okay. And yeah, so this is a possible example. Now, given any such string alpha, this stands for a Turing machine, even when it is invalid by our convention. And let us call that machine M subscript alpha. Okay. If it is a valid encoding, it is actually a machine. Otherwise, it's that particular machine, which immediately rejects and halts. Okay. So this is one thing. Likewise, every such string alpha can be treated as an input, And let us denote that input by X subscript alpha. To understand, this is originating from the string alpha, binary string alpha. Happy? But then, since alpha 1, alpha 2, alpha 3, dot, 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 this is an exhaustive list of all binary strings. This is also an exhaustive list of all Turing machines and all inputs. So every Turing machine, if encoded properly, will appear as some alpha. Not necessarily uniquely, but that doesn't matter. Okay. So this is the important thing. There are repetitions in this list, but the important thing is that there are no other Turing machines. Agree or not? Okay. Likewise, the same thing I can say about the inputs. Alpha 1, alpha 2, alpha 3 is an exhaustive list of all inputs. Again, there may be repetitions, but there are no other inputs. Happy? Okay. So with this understanding of strings as binary strings, as machines, and also as inputs, let us proceed to the proof itself. Okay. So it's a proof by contradiction. Suppose that the halting problem is decidable, or the language HP is recursive. Then there will be a total Turing machine D for HP. U is also having the U, or U prime is also having the same language, but it's not a decider, it's a recognizer. But let's think of a hypothetical decider D for solving the halting problem. Okay. So what does this D do? Given some encoding of M and some input X for M, it will decide in finite time whether M is going to halt on X or not. Okay, it's a decider. So for every M and for every X, this machine D can decide whether M halts on X or not in a finite amount of time. Okay. So that's the second sentence. Given any two binary strings, alpha I and alpha j, the hypothetical machine D decides in finite time whether M alpha I halts on X alpha j. Okay. Now consider this table. So as row headers, I list all the strings, binary strings, and on the as column headers, I also list all the binary strings. Alpha 1, alpha 2, alpha 3, and so on. They exhaustively list all possible strings. And I will treat this exhaustive listing in the row headers as machines, and as column headers, they are treated as inputs. Okay. So this is an exhaustive listing of all strings. This is also an exhaustive listing of all strings. Okay. As row headers, I consider these as machines. As column headers, I consider these as inputs. Okay. And then it makes sense to talk about some ijth entry. If M alpha I halts on alpha j, X alpha j, then that entry of that infinite two-dimensional table is H, means halt. If M alpha I does not halt on X alpha j, then the ijth entry of the table is L, meaning loop. Okay. So H stands for halt, L stands for loop. Okay. And the idea is that since D is a decider for the halting problem, given any I and j or any alpha I and alpha j, it can compute the ijth entry, whether it is H or agree. So now this is where the diagonalization thing is coming. Okay, this is an infinite listing. Now I look at the diagonal of this table. This is H, so I change it to L. If this is L, I change it to H. This is H, I change it to L. If this is H, I also change it to L. Okay. And what I am going to do is that I will design a Turing machine E which exhibits exactly this blue colored halting pattern on all inputs. Okay. And that will lead to a contradiction, as we will see. Okay. So I am now going to design a Turing machine E, which on input alpha 1 or X alpha 1 loops, on X alpha 2 halts, on X alpha 3 loops, and so on, provided this is the behavior of the other machines. Okay. So I will now use D to generate a Turing machine E. Okay. Now E takes a single binary string alpha as input. Okay. Not two things, M alpha I and X alpha j. Instead, it takes just alpha, a single string alpha as input. And this alpha stands for both a Turing machine and an input. Okay. Whether valid or not, doesn't matter. Okay. So E generates the input alpha hash alpha by copying it and feeds that alpha hash alpha to D. Essentially, that means D is a decider. Okay. Now this E may have all the transitions of D in its own CPU, in its own head, in its own finite control, or it can proceed as the universal Turing machine does. Okay, maybe on some tape, it has the description of D, and the input is alpha hash alpha. Okay, and it will keep on simulate D on the string alpha hash alpha. But D is a decider. So whatever input it is fed, it is fed. It will say loop or halt in a finite amount of time. Okay. So he simulates D on this input alpha hash alpha, and D is a decider. So a finite time simulation gives the answer H or L. H is halt. Okay. Halt means accept. Loop means reject. No, it does not halt. Okay. Then what E does, if D outputs halt, E goes to an infinite loop. Okay, like always move right. Whatever you see, you keep on moving right in some non-looping state, non-halting state. Okay, in a looping state. On the other hand, if D outputs L, then E immediately halts. Maybe after accepting or rejecting, that doesn't matter because we are now talking about the halting behavior. Okay, so it may accept and halt or reject and halt, but it halts immediately. Okay. Now comes the final part of the proof. If D exists, I can convert D to a Turing machine E. E is a valid Turing machine. Okay. So it must be equal to M alpha n. It has some encoding. Okay. And we have seen that we have all possible encodings of Turing machines as row headers. There are no other Turing machines. So E is a Turing machine, so it will appear. Agree? Okay, so let's say, again, the encoding of E is not necessarily unique, but pick any encoding of E and let us call it alpha n. For some n, it will have to happen. Okay. And then the rows, we are talking about the same Turing machine, M alpha n and E. So their halting and looping pattern must be identical on all inputs. Right? The two rows must be identical. But the way I have generated the row for E indicates that as the nth element, their behavior is different. Right? In other words, if D says halt, E will not halt. Okay, so if E halts, D says that E halts, you will actually enter an infinite loop. And if D says E does not halt, E will actually halt. This is not possible, right? Okay. So you can also just look at the rows, M alpha n and E must be identical, but the rows must differ in the nth column. On the other entries may be equal, may be unequal. Okay. For example, if you look at this picture, yeah, this is M alpha n, this is E, L, L. Accidentally, they may be equal. H, they may also be equal. Here it is not equal, but they may be equal. But this entry and this entry must be unequal. Okay, so these two rows cannot be identical. Even if all other entries are accidentally same, they must differ at least one position, the nth position. Okay. Now the rows must differ in the nth column, and this immediately leads to a contradiction. And why did that contradiction arise? It is because we assume that a hypothetical decider D exists. In particular, this contradiction says that E cannot exist, and the existence of E depends upon the existence of D. So D cannot also exist. Okay. So E cannot exist, and consequently, D also cannot exist. So the halting problem cannot have a decider. Okay. So that's the diagonalization proof. In this form or some other equivalent form, Turing proposed this proof, definitely based upon Cantor's diagonalization idea. Okay. Possibly Turing didn't present it in this form itself, but the proof is essentially this. This is how modern textbooks write the proof. Okay. Yeah. So that's it. Okay. So this is the first example of a non-recursive problem that you see. Okay. and you may just convert this to a proof, the diagonalization proof that the membership problem is not decided. Okay. And then what we are now going to do is following another idea to prove undecidable problems, because diagonalization proofs are somewhat complicated, okay, and not necessarily very easy to do for any language, any undecidable language. Okay, so we use another technique called reduction. So let us have a small break, then I will start this. Okay. So let us now see a different kind of argument to prove undecidability. Of course, we will always start with the fact that the halting problem is undecidable. We have to use this result. And anyway, the implication of this is pretty unsettling, I would say. So first of all, Cantor like arguments like diagonalization, which is essentially countability uncountability thing. And it essentially proves that there must be undecidable problems. Okay, so all problems cannot be solved. There must be undecidable problems. This also follows from so-called Gödel's incompleteness theorem. Okay. Every system of reasoning will have some statements that are true but cannot be proved. This kind of statement. But Turing makes this thing even worse. Okay. In fact, near the end of these slides, we will see that given a problem, or maybe in the next slide, this slide itself anyway, given a problem, it is undecidable whether that problem is decidable or not. Okay. In fact, the problem of deciding whether, or problem of understanding whether some problem is decidable or not, is not even Turing recognizing. Okay, so that is how reality is. Okay, so given a problem which I want to solve, and I see that it is taking too much time, there are two things, two possibilities. The problem is very difficult problem. That is why I am taking so much time to solve it. Another possibility is that that problem is not even solvable. How can I solve it? And Turing says that there is no general way of distinguishing between these two things. The problem is taking pretty long because it is not solvable, or it's a difficult problem. You cannot say even that. Finding? Yes. This is the same thing as the halting problem, essentially. But because these machines are mathematical, so I mean, reasoning on these machines is much simpler than your C programs or RAM machines, computers. It is exactly the same thing. Okay, the halting problem. Okay, so let us see. Okay, so we have actually seen all these things. Let me skip. We have these two problems. They are Turing recognizable, but no decider can exist for HP or MP, no matter how intelligent Turing machines can be. Okay. Okay, so I can make a similar diagonalization argument. So instead of H and L, I will just write accept and reject, A and R, okay, in that two-dimensional table. Now what I will do is I will now use the theory of reduction to prove that the membership problem is undecidable. Okay. So this reduction works as follows. Once again, it's a proof by contradiction. Assume that the membership problem is decidable. So it has a decider shown like this. This is a hypothetical decider. Okay. Then what I will do, I will use a reduction algorithm that converts an input for the halting problem to an input for the membership problem. Okay. So what do I mean by this? It says that this reduction algorithm should ensure that M halts on W if and only if N accepts V. Okay. So that should be the correctness of reduction. Otherwise, this reduction makes no sense. Okay. And more importantly, this reduction must be doable by a total Turing machine. So this reduction algorithm is a Turing machine that given any input will supply an output. It's not a yes no kind of decision making machine. It's a kind of converting input of one problem to the input of another problem. Okay. That satisfies the property. In this case, this reduction must satisfy that M halts on W if and only if N accepts V. Okay. Now, if such a reduction algorithm exists, then this, in tandem with the hypothetical decider for MP, will give me a decider for HP. That dotted box. But by a diagonalization argument, we have already proved that no decider for HP can exist. And therefore, that box, the decider for MP, that is also non-existent. Okay. Okay. Yeah, that's also possible that there are two things. Either the reduction algorithm does not exist or the decider does not exist. Okay. But I will just now construct that reduction algorithm. Okay. So that exists. Therefore, the only problem is the assumption that the decider for MP does exist. Okay. Yes. But this dotted box cannot exist. That is because so this will prove that this reduction algorithm actually exists. So the only problem is this decider for MP cannot exist, and therefore MP is also an undecidable problem. Okay. So I want to prove the undecidability of the membership problem. A reduction algorithm converts an input M hash W for HP to an input N hash V for MP. And this algorithm must be the work of a total Turing machine. Okay. And that is the correctness of reduction. N accepts V if and only if M halts on W. Okay. And yeah, so if MP has a decider D, then this reduction algorithm followed by D gives me a decider for HP, and that is a contradiction. So D cannot exist. Okay. Okay, so let me now tell the reduction algorithm. So input is M and W, output is N and V. Okay. And this is the these are the steps. So input M and W are provided in some encoded form. Okay. So the so-called reduction Turing machine will convert the description of M to the description of N. In fact, it will take W equal to V, so it's just a case of copying. Okay. So what does this do? So add a new accept state T prime and a new reject state R prime to M. So by looking at the encoding, the reduction machine knows how many states are there, some N states are there. It simply replaces that thing by n plus 2. Okay. And it introduces two new states. Let's say it gives the number n to t prime, n plus 1 to r prime. This is one possibility. Okay. So it will change the description of t and r to t prime and r prime in that description. Okay. That is also doable. And since t prime and r prime are new accept and reject states, the old t and r must be non-halting. Okay. That can be recorded in the description. Also, you add transitions of this form. If m ever enters t or r, okay, then this converted machine will enter t prime. Okay. And there is no way you can enter r prime. So all rejection is by explicit looping, implicit rejection, right? If it is accept t, then also you go to accept. If it is reject, then also you go to accept. So the only way this machine n can reject is by looping. Okay. Take v equal to w. And I leave it to your understanding that a total Turing machine given m and w can generate n and v in a finite amount of time by simply looking at the encoding. Okay. Yeah.
N equal to loop time, the one which has the faulting problem, and V equal to hash W.
So your suggestion is n equal to okay, so let us see. Your suggestion is n equal to u prime and v equal to m hash w. Then u prime halts on m hash w if and only if m halts on w. Yeah, maybe that will also work. Yes, possibly that will work. But anyway, you will have to figure out that u prime. But sometimes in some reductions, I will use this u. Okay. Yeah, looks legit. Looks legit. Okay, so whatever. Anyway, the reduction algorithm is not really unique. Okay, but this will also work, right? Okay. So there is no way n can enter r prime, and therefore all kind of rejection is by looping. Okay. So m halts after accepting or rejecting, and if that thing happens by entering state t or r, then n just runs for one more step to enter the new accept state t prime, and it accepts. Okay. And if m loops on w, n also loops on w. On v, which is same as w. Therefore, this reduction algorithm is correct. M halts on w if and only if n accepts v. Happy? Okay. So by a diagonalization argument, you can prove MP to be undecidable, or you can use reduction from HP. So this is the important thing for a reduction. You should never forget. You reduce from a problem which is already known to be undecidable to a problem of which the undecidability is to be proved. So the direction is very, very important. Okay. So this direction of reduction. This will keep on bugging you even in future. In algorithms too, when we prove certain languages to be, or certain problems to be NP hard, we start from a known NP hard problem, make a reduction to a new problem, which you prove to be to a new problem. Okay. For example, I can also have a reduction from MP to HP. Okay. So this algorithm is given here. You can just figure out that this is correct. And suppose that I know HP to be undecidable, but this reduction does not imply that MP is undecidable. Why? Because this reduction gives one way of solving MP. Okay. There may be other ways of solving MP without reducing to HP. Okay. Therefore, this reduction goes in the wrong direction. Okay. From a new problem to a known problem, this reduction is a fine. You can construct this reduction, but this gives us a way of solving the new problem. You cannot prove that this is the only way of solving the new problem. Okay, so this reduction is therefore very, very important. So this is not an undecidability proof for MP, because a decider of MP is not forced to use a hypothetical decider for HP. There may be other ways of solving it. Right? In particular, however, if I somehow know that MP is undecidable, then this reduction will prove that HP is undecidable. Okay. So that way also you can proceed. If MP was proved to be undecidable, this reduction proves that HP is undecidable. It's not the other way around. Okay. Okay. So with this example, the first example of reduction in hand, let me formally define what is meant by reduction. Suppose that A is a language over some alphabet sigma, and B is a language over some alphabet lambda, as shown in the picture. Okay, a reduction algorithm from A to B is a map from sigma star to lambda star. Okay, such that elements of A will map to elements of B, as the picture shows, and elements not in A will map to elements not in B. So it's a map from this entire sigma star to entire lambda star, such that elements inside this language A will go to elements inside this B. Elements outside A will go to elements outside B. Okay. So, okay, in words, let A and B be two languages. Consider a map, sigma, from the entire of sigma star to lambda star. Okay. If W is in A, then the image will be in B. If W is not in A, that is the complement of A, then its image will also be in the complement of B. Okay. This is an important thing. Sigma need not be injective, it need not be surjective, it need not be bijective. Nothing like that is demanded. Okay. The only property is that it maps elements of that language to the elements of the target language and non-elements to non-elements. No other functional property is needed. Injectivity, bijectivity, and all that stuff. In particular, you can see, for example, that this maps to this maps to this, and so on. But this is perfectly okay in terms of reduction. Okay. And for a reduction to be useful in the undecidability proofs, must be computable by a total Turing machine. The map sigma must be computed by a total Turing machine. So given the input, it will generate the image in a finite amount of time, and that should be true for any to that reduction algorithm. Agree? Otherwise, the question that was raised, if there is no reduction algorithm, then also that proof fails, right? MP is undecidable. That proof fails for two reasons. No reduction algorithm exists, or no decider for HP exists. MP exists. Okay, so a total Turing machine must implement on every input W, the reduction machine R, which is not basically an accept reject kind of machine, but it does something, some computation. Okay. It halts after correctly computing this. And we call this R a reduction algorithm. Okay. Anything else? We say that sigma is a reduction from A to B. Okay. And we write this as A less than equal to B. And sometimes we use that subscript M to imply that this is a many to one reduction. Okay. So why many to one? Because multiple inputs may map to the same image. Okay. That's possible. And that reduction may also be an injective map, but anyway, we allow this map to be non-injective, and therefore we talk about this many to one reduction. We talk about the possibility of having non-injective maps. Okay. In fact, there are other kinds of reduction. One is called Turing reduction, but you don't need to worry about those things for the moment. And we often do not write this underscore M because this is the only notion of reduction that we will study in this course. Okay. So why is this less than equal to sign? Size is not important. Size is not important. The reduction algorithm gives a way to solve A, given a way to solve B. Okay. Therefore, but A can be solved by other methods. Okay. So this less than equal to sign essentially says that the problem A is no more difficult than B. Okay. The problem P is no more difficult than, the problem A is no more difficult than the problem B. Because if I can solve B, I can solve A. Happy? Okay. So the membership problem for A is no more difficult than the membership problem for B, and that is why we use the less than equal to sign. Okay. And we have seen the halting problem reduces to the membership problem. And we have also seen a reduction that the membership problem reduces to the halting problem. Okay. Okay. So before we look at some other examples, let us see. First of all, languages and problems are essentially the same thing. Okay. So L is a language, the corresponding problem is this. Given a string W, it is the membership problem whether W is in L. Okay. In that sense, languages and problems are essentially the same. Okay. And we talk about two things, reducing one language to another, but usually we say reducing one problem to another problem, with this identification of problems with languages. Okay. And if there are problems P and Q, we can write this way. Okay. So a reduction algorithm is supposed to convert an instance of P to an instance of Q. And also, I mean, with respect to membership, if that problem is solvable for some input, the converted install will also solve Q. The problem, target problem, and converse. This is very, very important. A reduction algorithm makes no effort to solve P or to solve Q. Its only task is converting instances of one problem to the instances of the target problem. It makes no attempt to solve P. It makes no attempt to solve Q. Happy? So then, how we can use reduction? First of all, look at this less than equal to sign. Okay. This says that if Q is easy, P is no more difficult than that, so P is also easy. Easy here, of course, means solvable, decidable, something like that. Okay. So the first use is this. Given a solver for Q, use this solver as a subroutine to solve P. Agree? But this is one way of solving P, not necessarily the best way or the most efficient way. So this does not prove any undecidability result. On the other hand, if I assume that P is difficult, Q is at least as difficult as P, Q is greater than or equal to P, so Q is also difficult. And difficult here means unsolvable or undecidable. Okay. So if no solver for P exists, then no solver for Q can also exist. Okay. We will typically use reductions in this sense. P is undecidable. By a reduction to Q, we will show that Q is also undecidable. Okay. So maybe I will give you just another example, because I have around 10 minutes. Okay, so we can look at this. Okay. So this is a very special instance of the membership problem. Okay. I am given an encoding of a Turing machine, and I am not asking the question that M halts or not on some input X. I just take a fixed X like epsilon. And the question is now a very more specific question. Whether M halts on epsilon or accepts epsilon. Okay. So earlier M hash X. Okay. And I am taking the special string epsilon for X and asking apparently the empty string. Okay. It's not that general question on any M and any X. The M is any, but that X is taken to be the special thing epsilon. So this is a special or restricted version of the membership problem, but it turns out even this problem is undecidable. Okay. So for undecidability proof, I will use reduction from HP. And for semi-decidability proofs that I will cover a little later in the next class on Monday, I will use reduction from the complement of HP. Anyway. Huh? A universal Turing machine cannot solve the general membership problem. Okay. But this is a special kind of membership problem. No, but if I make the input something special, this may be some special instance. Right? And may be solvable. This we cannot immediately conclude without a proper proof. Right? Because true. We have proved it for any string X. But I am now talking about a special version of it. And that special version may be solvable. Fixed X, yes. Okay. So unless I prove this, I cannot accept. Because that general problem is undecidable. But I am talking about a special instance of that problem, special subclass of that problem, which may be easy. Right? But it turns out that that special thing is also unsolvable, undecidable. Okay. And that needs a proof. But of course, if you go to a more general version, then of course you can use that undecidability of the membership problem or the halting problem. But now I am working on a special instance, special case, which requires a proof. So I will start from HP. I will start from HP, whose instances are of the form M, W or M hash W. And the output is an instance for this new problem where the input is epsilon. I do not need to explicitly mention epsilon. So I will just produce a Turing machine N. Okay. So the earlier reduction essentially used all these transitions of M, right? That N, the target machine that we generated, uses all the reductions of M. Not reductions, all the transitions of M, plus some additional transitions. The jumping from T and R to T prime. Okay. So that reduction algorithm, what it does, it embeds the information about M and W, okay, in the finite control of the target machine. Okay. So this is what the picture says. The new machine N can have all the transitions of M. Okay. It can also have the information on W. So this is finite amount of information and can be embedded in the finite control of N. And its input is basically epsilon. Whatever it does on other inputs, that is not of a big concern to us. Okay. So now let's see. So it suffices that I give a description of N. What N does when it is provided with some input YV, something like that. It has embedded in it finite control M and W. Okay. So input is M and W, and the output is a Turing machine N that accepts epsilon if and only if M halts on W. Okay. So N can use M and W in any manner it likes. Okay. Maybe these things are embedded in the finite control, which essentially means N knows all the transitions of M. Or it can write the description of M and W on a tape, second tape, third tape, something like that. So that is another possibility. Okay. So it starts this machine N with a description of M and W on some tape or in the head. Okay. So now I have to say how N behaves when it gets an input V. V has nothing to do with W. The question is about the halting behavior of M on W, but N has an independent input. M and W are not part of the input. It is either part of the finite control or written as an auxiliary information on a second tape, third tape, something like that. Okay. Hmm? Yes, yes. Do something like you, whatever you does. So it can simulate that universal Turing machine, or it has the information about M in the finite control itself. So it can also follow its finite control, whatever. Okay. So what it does, it erases input V, write the string W on the tape from the finite control, or if it is there on another tape, bring it to the first step maybe. Okay. And then simulate M on W. Okay. That simulation can be of two types, either an UTM-like simulation, or if the transitions are already embedded in the finite control, follow your own transitions. Right. If the simulation halts, you accept V. That's all. So what does this reduction algorithm guarantees? N accepts its input if and only if M halts on W. Okay? You can see that if M halts on W, the simulation halts, then you are going to accept V. And if the simulation does not halt, this machine N will continue to stay in this step 3 or phase 3. It will never come and do any accept or reject decision. Okay? So that's what is meant by this. N accepts its input V if and only if M halts on W. Okay. In particular, if M halts on W, then whatever that input V is, it is going to accept. Not only epsilon, everything. Right? That doesn't matter. Because the question is about the acceptance of epsilon and other strings, whether they are accepted or not, that's not part of the question. And we don't care. Okay. So if M halts on W, N accepts everything. So its language is sigma star. If M does not halt on W, it gets stuck in phase 3. It accepts nothing. Okay. So in particular, epsilon belongs here, sigma star, but epsilon does not belong to the empty set pi. Epsilon is a member of this, but not of this. Okay. Okay, but okay. In particular, N accepts epsilon if and only if N halts on W. But maybe I just tell you some. The same reduction also proves many things, because just think of that two behavior, sigma star and empty. Okay. So it also decides these problems. Okay. Or it proves that these problems are also undecidable. If instead of epsilon, we take any fixed string W, this belongs to sigma star, but not in the empty set. Okay. So I can take that. Given any fixed string W, the problem whether the Turing machine M accepts W is undecidable. The problem whether a given Turing machine accepts any string at all, that is same reduction, right? In one case, it accepting everything. In the other case, it is not accepting anything. Some reduction can be used to do this proof. Likewise, whether it accepts anything, any string or all strings, same reduction will work, right? And the problem whether a given Turing machine can accepts only finitely many strings. This is also solvable. This is also proved by this reduction, because the empty set is finite, size 0, and sigma star is infinite. Okay. Okay. So this is actually going to be the most difficult set of concepts in this entire course. So we will study the reduction things and prove something called Rice's theorem in the next week. And yeah, so we will study these things carefully. Okay. Okay, so let us stop today. It's already a long session. Okay, so that's it.